see here. All right. So I'm going to go ahead and start the lab portion, which is the tracing of that factorial program. Okay. All right, so here's the factorial program, and the mysterious part is what do we do on line 5 when n as a parameter is actually greater than 1? Because if it's greater than 1, we evaluate and execute the true value, which is the middle part, the stuff that is between the question mark and the colon. And in that expression, it also wants to invoke f with the value of n minus 1. Okay, so that really is the big mystery. It's like, what do we do on line 5? Okay, so what we'll do is we'll compile the program and link the program, and then we'll run it in GDB very slowly and using a lot of BT and single stepping. Okay. So G++ dash model dash tick dash G dash C. Later on, I'll talk about how to make it easier to compile and link the program. Just a simple warning, same stuff that we have been getting all day long. So no big deal there. And we'll go ahead and link the program, and now we can run it. All right, so once we can run the program, we'll put a breakpoint on line 12, which is really not mysterious. Okay, that's not the part that is kind of mysterious. So we are now on line 12. I just ran the program, and we are now on line 12. So on line 12, well, it's kind of the same thing as before. We invoke the subroutine f, right? So we'll end up inside, subroutine f from line 12. Okay, single step, just as we predicted. Now this time, but when we do a BT this time, it's going to show us something that did not show us last time. Okay, so when we do a BT, we can tell that pound 1, which is also called frame 1. Okay, so we'll talk about what a frame is later on. But when we look at pound 1, it doesn't really appear any different from last time. It shows us that we got here from line 12 of main as a subroutine, and we are current from factorial.cpp, which is the source file. No big deal, same stuff that we have seen before. But when we look at pound 0, there's something new this time, right? Because we have been using 5 as a subroutine, which did not use any parameters. But this time, f as a subroutine does have one parameter n. And it shows us that n is 3. Wow. Well, that by itself doesn't seem to be very, groundbreaking. It's like, okay, we know that because when we call f, we call f with an argument of 3. So it's not really a big surprise that the parameter n has the same value as the argument. Okay, no big deal. And we are now on line 5, which is where the recursion is. On line 5, we know that the 3 is greater than 1 is true, right? So that means n is greater than 1 will give us a value of non-zero. If that is non-zero, we'll go ahead and evaluate the true value. The true value will take this n, which is 3, and multiply that by whatever f of n minus 1 is going to return. So we are going to invoke f again. But what is the argument to the second invocation of f? Come on, you guys have to answer the question. What is the argument that we will pass to f in the second invocation of f? 2, exactly. Because n is currently 3. 3 minus 1 is 2. So that's how we will call f the second time. Okay? So when we single step, we'll end up on the same line again, which is awfully confusing, right? We went from line 5 to line 5. But that's easy to explain actually. Because on line 5, the previous one, we have to invoke f again. But when we invoke f, we end up on line 5 again. Is that okay so far? Okay. All right. So we're on line 5 again, and you can also see that f in open parentheses here, open parentheses, n equals 2. So it does know that we are now in a different invocation of f, where parameter n is now 2. But what about that 3 that we had earlier? Did we lose it or something? I mean, where is it? Do a backtrace. Okay? Now this is the magic of subroutines. It's because when you do a backtrace, we didn't lose anything. Okay? We are now in the second invocation of F, but it actually keeps track of the first one as well. Are you guys kind of seeing what's happening here? Every time you invoke or every time you call a subroutine, it starts off a quote-unquote new instance. It starts off a new lease, a new contract, just like with a U-Haul truck. Okay? And it keeps track of a stack of these things too. Now when I use the word stack in this class, I'm kind of using it in a very loose sense, not in the sense of a stack in computer programming, which has a very specific meaning. So we're basically keeping track of a stack of these invocations. And you can call F as many times as you want, and it will keep track of every single invocation separately. Are we still doing okay so far with this concept? Okay. So we are now currently in the second invocation of F, and n as a parameter has a value of 2. And we are going to evaluate the expression on line 5. 2 is greater than 1 is true. So that means we're going to reevaluate the middle part of line 5, which means we're going to reevaluate n, but this time n is 2. And then we'll call F again with 2 minus 1, which is 1, as its argument. Are we doing okay so far with this? So when we single step, where am I supposed to end up at? Which line? Line 5 again. And sure enough, we are now back onto line 5. But this is not the same as before, because this time you can see that parameter n now has a value of 1, not 2, not 3. What happened to n equals to 2 and n equals to 3? What happened to all the other invocations of F? Don't worry, they're still here. Do a BT, and you can see how we got here. So when you look at BT, and the result of BT, this clearly states how we got here. Main on line 12 calls F. F on line 5 calls F. F on line 5 calls F again, and this is where we are. Yep.
So when you run line 5 initially, you have the value 3, and then when you get the second one where it's F of n minus 1, that tells you to redo line 5 again?
Every time you call a subroutine, you always start from the very beginning of a subroutine. So regardless of where the invocation is, okay, you can have the invocation in main, you can have the invocation in subroutine G if we had a subroutine G, or you can have the invocation in subroutine F itself. It would still do the same thing, which is going to continue. It will continue execution in the subroutine that you're calling, and it will always start from the beginning. And that's what we are seeing here, because line 5 is the only line which is also the beginning of the entire subroutine. Okay? Now, but this time, because n equals to 1, parameter n is 1, n is greater than 1 is false, okay, or 0, okay? So which expression is it going to evaluate? 1, right? Does 1 involve invoking F again? Nope, just a constant, right? So this one is going to be returned, and where are we going back to? According to ET, how did I get here? We got here from line 5, so we're going to go back to line 5. Hold on a second here. When we get back to line 5, which line 5 are we talking about? There's only one line 5. But when we get back to that line 5, okay, we'll single step. Now we're at the end of the last invocation. When you do a BT, it will clearly state that we are now in the last or the third invocation of F. When you single step one more time, we're now back to line 6. But if you do a BT, it shows you where we are now at. We are now at the end of the second invocation of F. Are we doing okay so far with that? A little bit? Okay. So we are now at the end of F, but this is the second invocation. In other words, the first subletter of your U-Haul truck is ready to return the truck. Okay? And when this returns, it will go back to the first invocation of f. Oops. And when you do a BT, we are now back to the first invocation. So when we're back to this invocation on line 6, it is going to return a value of 6 because the previous one returns a 1. 1 times 2 is 2, and then this time 2 times 3 is going to be 6. So when we return it one more time, it's going to be 6. So single step and print the value of x. It is actually 6. Now, if you want this program to be a little bit more clear, we can actually make it a little bit longer, but it'll be more clear that way. So let's go ahead and make it a little bit more clear. So instead of using return and the ternary operator on the same line, I'm going to do it like this. Okay, so I'm going to make a. I would like to use x again, but let's not throw another wrench into this whole thing. So I'm just going to use a local variable y in this case, and we'll say return y here. Okay, so it's basically doing the same thing as last time, but it will be more clear as to where we're returning to and which y is getting updated. Are we doing okay so far with this code? Does everybody kind of see that this is really the same thing as the previous program? Okay, because y is really not needed because we put some value into it and then we just return that same value right away. But this way it is easier to see how recursion works. Okay, so we'll go ahead and recompile the program. And 219, 220, and 221. All right, same thing as last time, single step, and now we are in the first invocation of f. Okay, so when you do a BT, same as last time, doesn't seem like there's a big deal here. Okay, and when we single step, it's going to the second invocation of f, just like last time. When we single step one more time, it will go to the last and third invocation of f. When you do a BT, it seems like nothing really has changed. Well, it actually has changed. Okay. What about y? Y is a local variable. How many y's do you think we have? We have 3. Okay. There's one n and one y per invocation. Okay. Now let me just repeat what I said. There's one n, which is a parameter, and one y, which is a local variable, per invocation, not per function. Okay, because the function is a U-Haul truck. N and y are basically things that get created when the function is being used. So you can kind of look at n and y in the U-Haul truck analogy as radio stations, the settings of a radio station or the settings of a rear mirror. So when you rent the truck, okay, you're going to set everything to your preferences, right? So you have your own parameter n and your own local variable y. When you sublet the truck to somebody else, that other person is going to customize those settings to that person's preference. But you don't want to lose your settings, do you? Right? Because you don't want that person to return the truck to you and everything is off. So that means there's a way to store your settings in the truck. So when the other person is done with the truck and return the truck back to you, the truck will, quote unquote, magically restore your settings. So it's basically storing your settings somewhere, within the settings of the truck. Is that analogy kind of working okay? So there's still only one truck, but the same truck can have multiple settings. You can also look at it this way. Okay, you have one U-Haul truck. I think this is probably the best way to look at it. Okay, so you have one truck. Oh, the wheel goes a little bit forward here, okay, like that. Okay. So there's only one truck, but inside the truck, there's a little notebook. Think about a notebook here. So inside the cabin, there's a notebook. The notebook has multiple pages. When the U-Haul truck is sitting on the lot of U-Haul, this notebook is empty because nobody is renting it, nobody is using it. So therefore, there's no need to put anything on the notebook itself. When you rent the truck, okay, then what you do is you write down your settings, your preferences. So you will write down your mirror settings, you write down your radio setting, preferences, the seat, length, and so on. So the first page of the notebook is now used to store your preferences because you're the first renter of this truck. Are we doing okay so far? When you sublet the truck to somebody else, guess what? The second person will go to the second page and write down the same information, but those would be the settings or preferences applicable to the second person, the subletter of the truck. When the second subletter, okay, the third person, ran the truck from the subletter, it would use up the third page. These pages, or the entries of each page, are the parameters and the local variables. There's only one truck, there's only one mirror, and there's only one radio. However, the settings, the preferences, there are multiple copies of those. Are we kind of seeing this okay, using this analogy? Okay. All right. Well, I claim that there are 3 ends, and the ends are easy to see because we can see there's one end here, there's one end here, there's one end here. They all have different values. Okay, fine. The ends are easy to deal with. What about the y's? What about the local variable y's? Okay, let's see. We can say print y, and this y is the y of the last invocation, or basically the third person who rented the truck here. Okay. Well, y has a really kind of funky value because we haven't really done a single thing about y. So let's go ahead and do something about this first. We are on line 6, we're about to execute line 6. N is 1 at this point. So n is greater than 1 is false. When the first expression is false, we will go ahead and use the last expression as the return value of the entire ternary operation, which is just 1. So when we single step and we look at y has a value of 1. Is this part okay? We are at the very last invocation at this point. Okay, now I said that there's 1 y per invocation, and there are 3 invocations, which implies there are 3 local variable y's. How can I see the other y's? Okay, and the answer is we can actually do it using GDB. We'll first do a BT. Okay, when you do a BT, these numbers are not really just for show. Okay, pound 0, pound 1, pound 2, pound 3. They're not really just to enumerate, there are 3 things before this. You can actually utilize these numbers in a command called frame, F-R-A-M-E, frame. And using frame, you can now basically say, okay, I know that I'm in the last invocation of F, but I want to examine something in the second invocation or the first invocation of F. You can actually do that. So you can basically utilize the same numbers here and say, I want to switch to this frame here. I want to switch to frame 1. And frame 1 has n being what again? You can actually tell, in frame 1, n as a parameter has a value of 2. Okay, so let's go ahead and print n first to confirm that we are in the right frame. We are in the right frame. What about y? Y has a value of 0. Okay, let's go to the first frame. Okay, the first frame, which is this one here. It's actually called frame 2 because it's 2 frames away from the current active frame. So we'll say frame 2, which switches all the way back to the first invocation of F. And we'll first confirm this is the right frame by printing n. N is 3, okay, which means we are currently in the first frame, or the first invocation of F. And we'll go ahead and print y. And you can now see that the 3 invocations all have different values in their y's. Are we doing okay so far with this analogy? Well, not analogy, but this actual trace, because it is you can visually see that each frame or each invocation has its own n and has its own y. Okay, let's switch back to the one that we are currently active in, which is frame 0. And we are ready to return y. What are we returning again? Now this time it's easy to see what value we're actually returning because I store that into a local variable first, and we can always examine the local variable before we execute the return statement. So we know for sure the last invocation, the third invocation, is returning a value of 1. Okay, fine. We'll return it. And single step, we're still in the last invocation or the last frame. Now we're back to the second frame. Okay, we're just about to execute the return statement of the second frame. But we'll go ahead and take a look at line 6 of the second frame. In the second frame, n is what? 2. Okay. So that means we are done with this one. So we did the 2 times 1 because the last invocation returned a value of 1. N is a parameter, has a value of 2. 2 times 1 is 2. So that means y at this point should have a value of 2. And we can confirm that. Okay, so let's go ahead and confirm that and say print y. Y does have a value of 2. So we are now ready to return a value of 2 to the first invocation. Single step, we are now back to the first invocation. When we're back to the first invocation, it would have executed this line already. But from the perspective of the first invocation of f, what is the value of n? 3. And we just returned 2 from the second invocation, right? So that means we have a product of 3 and 2, which is 6. And we store that 6 into y on line 6. We are now ready to execute line 7. So the value in y is supposed to be 6. Okay, so we can confirm that. We can just go ahead and print y, and it is in fact 6. And then we can single step, and now we are getting all the way back to main. And in main, we are now ready to execute. Oh, not yet. Okay, we're still. Okay, now we're in main. We have just executed line 14, which means local variable x in main should now be 6. So let's go ahead and print that. Print x. It is now 6. Are there any questions about this trace? Yep.
Question.
Mhm.
So every time you initiate f on line 5 again, it comes back, it assigns the value to y every single time?
Yes. Because every time you continue execution on line 6, unless n is 1 or less, okay, you'll be coming back from another invocation of f, so you'll be utilizing the return value of that invocation of f and n, your own parameter, figure out the product of those two, and then the product is stored in y. The only time that does not apply is when n is less than or equal to 1, then the entire ternary operator is just returning a constant of 1, and you're all done. Okay. Are there any questions about this trace? Because this can be confusing. Yep.
Just curious, how does the program know how again to multiply all the results that we got for the y values and then get us like the final result?
How does the program do that?
Yeah. How does it know how to actually multiply? Because we did talk about like how he combines all the y values again and then give us the final result for the function, for the factorial function. I'm not sure if my question is.
Let me see if I can answer your question. So the question is, if I go back to the source code, so the question is, how does the program relate the y from here to, excuse me, the invocation of the previous invocation? Is that kind of the question?
Yeah, because for every invocation we get a different value for y.
Yes.
First
Well, we have a
invocation.
different y, which may or may not be the same value.
Yes. So the factorial, for example, 3 factorial is 6, right?
Yes. Mm-hmm.
So then the function, like by the end, we should get a result of 6, right?
Yes.
So how do we get it by the end?
We got 6 this time because, okay, the one way to look at this, which is not really a good way to look at it, because it can be confusing, it can lead to, a misunderstanding of the concepts, okay? So what we are really doing is to look at factorial in a recursive way. In other words, we look at factorial in its own definition is based on a number and a factorial of a smaller number. So we'll go ahead and take a look at how that works. So let's take a look at a concrete example of 5 factorial. Now, most of you know what factorial is. 5 factorial is 5 times 4 times 3 times 2 times 1. Okay? So 5 times 4 times 3 times 2 times 1, we know that. But when you look at 4 times 3 times 2 times 1, what does it resemble? 4 factorial. Okay, it does not resemble, it is 4 factorial. So 5 factorial is 5 times 4 factorial. So in general, you can do something about this, and you can say that n factorial is n times n minus 1 factorial. And so what happens is, when we are dealing with 3 factorial, we look at 3 factorial and say, oh, this is the same thing as 3 times 2 factorial. And then we ask the question, oh, what is 2 factorial? We apply the same mechanism. So we say, oh, you know what? I know what 2 factorial is. It is 2 times 1 factorial. And then we look at 1 factorial, and then we say, by definition, 0 and 1 factorial is 1. But because there's only one way you can rearrange one thing. And there's only one way you can rearrange 0 things. So that's why 0 factorial is actually defined to be 1. Is that kind of answering your question?
Yeah, because I know that's how it's like the function, how that's the function of the factorial, but how does the program actually do it by the end? Like, how does the program multiply the 5 times 4 times 3 times 2? Right?
Okay, the program does that by linking the value that you return from one invocation to the place where it was invoked in the previous invocation.
Okay, so
the link is coming from the return statement of the last invocation to the invocation of f in the second last invocation. So whatever value you specify here will end up being here in the previous invocation. And that's how those things are linked together.
Okay, but so we don't really see it like when we do the tracing. It just does it on, like in the
That is
background.
correct, because because it didn't stop on line 6.
Yeah.
And if it did it didn't stop on line 6 because line 6 is really just one single expression. So it didn't really stop where I wanted to stop to show you, hey, see, look at f of n minus 1. It actually has this value. Any other questions? How about you guys? Do you guys have any questions I can answer? No, go ahead.
Oh no, I was just. It's okay.
Okay, go ahead.
So I think I figured it out. So it goes through the process of line 6, and then it executes and invokes and invokes and invokes. And then when it comes back, you have n equals 1, n equals 2, n equals 3. And it does
Y equals 1. Oh, yeah, n is 3, 2, and 1. Yep.
So every time it executes those, it assigns that value of y.
Yes, but each invocation has its own y, and that's why we never mess up the y's of the other ones. Yeah, each invocation has its own. Now this is the biggest problem that I think people have, is when people look at a program like this from line 3 to line 8, most people think, oh, we have one parameter n and we have one parameter y, or local variable y. But that really is not the case, okay? Unless subroutine f is called or invoked from somewhere, there's none, okay? If I take this line out altogether, okay, let me illustrate the concept here. If I take this line out altogether, when I run this program, there'll be no parameter n and no local variable y. Because even though the U-Haul truck is sitting in the lot, no one is making use of the notebook in the U-Haul truck because nobody is renting the U-Haul truck. Okay? So all of these things, the parameter n and the local variable y, are basically allocated and used on the fly. As soon as an invocation is done, as soon as you return the truck, that page becomes blank again. It can be reused by another renter. So all of those things are basically created on the fly, and they're also destroyed on the fly when the invocation is done. So if there's one thing you want to remember, it is this, okay? Local variables and parameters are on a per invocation basis, not on a per function basis. A function definition is static. Invocations are dynamic. They are runtime behavior as opposed to compile time static definitions. So that if you understand that statement and you go like, okay, I get it, then you get recursion. The most serious problem about recursion is people do not understand that part, and they think there's only one n and there's only one y, and obviously this cannot work if there's only one of them. Are there any questions about this code? Now, if you want this code to be even more clear, there's one way to do it too. So you can modify this code a little bit more, and you can say y gets n first, and then in the second one, you can do it like this. Okay, this will still work unless you give it the factorial of 0. Okay, but this will still work, and you can just get rid of n times on this side. So it gives you something to track when you do a backtrace, because this time, every time you backtrace and look at different frame, y will have the same value as n, and you can easily see that there are 3 y's and there are 3 n's when you're in the last invocation. Any questions about this? No questions? Nobody's thinking, why would somebody think about stuff like this? What is the actual practical application of a subroutine calling itself, right? I mean, it doesn't seem to make sense to have any actual practical application of anything like this.
Actually know that you can use subroutines to actually save time. For example, if you the factorial function. If you know that in your program you're gonna recall the factorial function many times, you don't want to write it for example 100 times. If your code is I don't know, 1 million lines, so it's probably gonna shorten it to.
Well, you can turn this into just a loop. Okay, we haven't really talked about loops yet, but we can turn this into a loop. But there are things that are inherently what we call recursive. In other words, you have something and it divides into smaller components, but each component, structurally speaking, looks just like the parent structure. And we deal with that all day long without even knowing it. How many people have done something with files on your hard drive or your external hard drive or portable thumb drive or whatever today? Okay, do you put everything into the root folder, like the very top level of your thumb drive? Okay, fine. I'm not talking to you. Okay, does anyone utilize the concept of a subfolder? Okay, so you can better organize all your files.
Yeah, I
okay,
do that all the time.
and that's basically inherently a quote-unquote recursive structure, because a folder can contain just regular files, but what else can it contain? Other subfolders. And what about those subfolders? They can also contain subfolders, right? So that is by itself a recursive structure, because a folder has the same structural shape as the parent folder that contains it, right? Okay, but what about the application of this? Okay, what happens when you delete a folder? Okay, let's take a look. So I'm not going to do it, I'm just going to illustrate it, because otherwise I'll be in big trouble. So I'm going to pick a drive that has a lot of subfolders, which is the internal hard drive, probably this one. And I'll pick up something that probably has a lot of subfolders. I think system, where is it? Windows probably has a lot of subfolders. Okay, so we'll go ahead and take a look at Windows. So if my objective is to delete the entire folder Windows, okay, most systems won't let you do it unless the folder is empty. So if Windows is empty, yes, go ahead and delete the whole folder. But if it's not empty, you cannot do it. So the first thing I want to do is to go into Windows and say, oh, it's not empty. Well, not only is it not empty, because I can easily delete all the actual files within Windows, but it also has subfolders. What do I do with all of these subfolders? I go into one and go maybe I can just nuke this one. You know what? What a bummer. It has its own subfolders. Click on this one, and it's empty. It's actually empty. Okay, pick another one. Okay, this one is not empty, and then I go here, and this one only has regular files. Now, regular files are easy to do, but you can just delete it by itself. So if I delete all of these 4 files, I can now go back to the previous folder and say, oh, en-us is now empty. I can now delete that folder, and I can delete these regular files easily. So when boot is empty, I can now go back to system32, and I can pick on another subfolder and do the same thing, right? How do you write an algorithm to do this? Well, if you do it recursively, it's not that big of a deal, right? Because you can say, for each thing in a folder, do the following. If that thing is a regular file, just delete it. If it is a folder, call the same subroutine that you're in, because the subroutine that you are in knows how to delete content in a folder. So you just have to call the same subroutine, but this time the folder is supposed to delete is not the folder that you're in. It is one of the subfolders that you want to nuke. Is that working out okay? Okay. So in programming, there are a lot of concepts like this. Okay, there are a lot of times when we encounter problems where you can break a big problem into smaller problems. But the nice thing is each sub-problem, each one of the smaller problem has the same nature, the same constraints, and the same characteristics as the bigger problem that you're trying to solve. So you can basically reapply the same technique to each smaller problem until it becomes trivial and it is solvable. And that's when you stop the recursion and then you back up to the previous level and finish up whatever needs to be done there. Are we doing okay so far in terms of why we have recursion and the value of recursion in programming? Is that okay? All right, one more thing. Okay, factorial is easy to do without using recursion, but there's another type of number that can be defined recursively, and it's a little bit harder to do it without recursion. It can be done, it's just harder. It's called Fibonacci. There we go. So when you go to Wikipedia and you look at the definition of Fibonacci, it is recursive. So right here it tells you that f of n is defined to be f of n minus 1 plus f of n minus 2. Okay, so by itself it is a recursive definition. When do we stop the recursion? When you get down to f of 1, by definition it is 1. When you get down to f of 2, it is by definition 1 as well, and that's when you stop. So you can write a subroutine for Fibonacci just like this, okay? And we don't even need to utilize anything else, okay? We don't need to utilize loops or conditional statements because we have ternary operator. Okay, so I'll just go ahead and quickly write the code corresponding to Fibonacci, just so that we have a better, another example of how to use recursion. So now I can display both the documentation and the code. So we'll go ahead and deal with Fibonacci here. And Fibonacci, and it only takes one parameter, which is n. And I use one single, well, I can break it up, if you want me to break it up, I can do that too. So I can break it up and say we have a local variable x to store the intermediate result here. So x equals 2, and I still have to use a ternary operator to help us, do the conditional part, okay? And the ternary operator will first ask the question, do we need recursion, okay? So what do we need to do recursion? What is the first n that requires the recursive definition? When n is?
The user?
No. When you look at the parameter n, okay, this subroutine is supposed to figure out what is the Fibonacci number corresponding to n. So when do we actually need the recursion and say, oh, okay, I need to ask Fibonacci again to figure out what is the f of...
Where n is bigger than 1?
3. But when it's 3, we need recursion. Okay, when it's greater than 2. So when n is greater than 2, then we'll rely on the recursive definition of Fibonacci. So it will be the fib of n minus 1 plus the fib of n minus 2. Okay, and you can see how it is resembling this part of the equation, right? Okay, so when n is less than or equal to 2, then it is not recursive. So if it is less than or equal to 2, well, there's a possibility it's a 0, but assuming I would not ask you to solve for the case when for the Fibonacci number of 1, which you need to know what is the 0 case, then we can just say that this is just 1. Oh, wrong window. This would just be a 1. Is that okay so far? Okay. And then we can just return x here. Now when you trace this, this is a little bit more fun than the previous one, okay? Especially when you want to track down what is the Fibonacci number of 4, because you have 2 recursion points. You have a recursion point on the left-hand side of the addition, and then when it gets back, you have another recursion point from the right-hand side of the addition. Okay. So in main, we'll call it y. So we'll just go ahead and figure out the Fibonacci number for 4 here, and then do a return 0. Okay. And do a g++ dash d dash c fib dot f.cpp. And I made a mistake. Cannot be used as a function. Oh, that's because when I define it, it says expected comma or semicolon before open parentheses. Oh, okay.
You did in32n.
Yeah, yep, instead of t. But you can see how the error message is kind of a little bit cryptic, but it does point out to be this name that is not defined. Thank you. So we'll do it again. G++ dash o f o. Dash. All right. So we'll put a breakpoint on line 14, and this is going to be a little bit longer. Okay. So we'll run the program. Already running the program. When we single step, it goes into line 6. N is 4 at this point, and let me just move this window up a little bit so we can all see. So N is 4 at this point. Now, because N is 4, 4 is greater than 2, we go for the true value of a ternary operator. But when we evaluate the true value of a ternary operator, it has an addition, but the most important part is it has 2 recursion points. So we'll go for the first recursion point first, and most of the time it's left to right, but there's no guarantee that in an addition it's going to go from right to left. So when I single step, this is confirmation that it is going from right to left. So now we're trying to figure out the Fibonacci number of 3. 3 is greater than 2, right? So we are now going to go for the recursion again, and this is going to go to f of 2. Now when we get to f of 2, it's easy because f of 2 is it will return the value of 1, which is correct. Okay. And then it will go back. Well, not yet. Okay, so with a single step, we print x is 1, and now it returns to the previous invocation. Now, when we do a BT, we can easily tell where we're going back to. So we're going back to the second invocation of fib, where n is 3. Okay, but with that one, it will go back again. Okay, so we are now exiting the third invocation, but from the third invocation, it's going to invoke again. With n equals to 1. In other words, it did not really stop on line 6 again, because now we are back onto the third invocation of fib, but this time n equals to 1 because it comes from the right-hand side of the addition of the previous invocation. Does everybody see how we got here? Because the reason why I'm here is because I got called from line 6 when n equals to 3. But this is the right-hand side of the addition, where it wants to know what is fib of n minus 2. When n is 3, n minus 2 is 1. Is that okay? Okay. So even though it did not really stop in the previous invocation, from the backtrace we can tell how we got here in the first place. Question? No, it's stretching. Okay. So are there any questions about recursion? How this stuff works? It may not sink in the first time, and that's why you might want to enter this particular program and go through the trace yourself and just try to figure out why is it doing this in the next step. And you can also make changes to the program too if you want to, to experiment with these programs. Are there any other questions? No other questions? Yep, go ahead.
So once it runs through the first sequence of Fibonacci n minus 1, it's going to go back to the second sequence on the right-hand side of the addition.
Right, because when it's done with this one, it will come back and it will say, hey, I cannot do the addition just yet because I need to know what is the right-hand side. But the right-hand side of the addition is another recursive call to Fibonacci. So that's why it has to call that again. When that returns, now you have two actual values that you can add. Then it will go ahead and add these two, store it into X, and then return the value of X.
So how are those values, there's so many of them, how are they going to add up? Or are they just going to be two final values?
Well, let's single step here. Okay, so let's single step through the case when n equals to 1. Okay, so when we single step, when n equals to 1, n is greater than 2 is false, and it will just return a 1, so the x becomes just 1, right? Oops. And x is 1. Now we're getting back to the previous invocation. In the previous invocation, it would have computed the left and the right-hand side already. Okay, when you do a BT, we can see that we're trying to figure out what is the Fibonacci number of n equals to 3. But we're already done with line 6. And what do you think should be in X right now? The left-hand side of the addition is trying to figure out f of 2, which is 1. The right-hand side of the addition is trying to figure out what is fib of 1, which is also 1. 1 plus 1 is 2. So at this point, X should be 2. Okay. So let's take a look. It is in fact 2. So when this is all done, we are going back to the invocation where n equals to 4. And we have figured out the left-hand side of the addition of that one, and then we'll try to figure out the right-hand side, which is f of 2. So it will call fib again to try to figure out what is fib of 2. So let's single step to confirm that. See, it is invoking f again, a fib again, to try to figure out what is the Fibonacci of n equals 2, and single step, x gets 1 because n is greater than 2 is false, so it will just return a 1, and that is going to be in X. So when we return X, we are now back to the first case. When you do a BT, we are now back to n equals to 4, which is going to be 2 plus 1, which is 3. So in this particular invocation, X should be 3 at this point. And then when you single step, the rest is not really interesting because it just returns to main, and then the local variable in main gets updated to 3. But when you look at the definition or the series, f of 4 is supposed to be 3. This is f of 0 in modern usage. Okay, so this is 1, 2, 3, 4. So the f of 4 is supposed to be 3. So we got the right answer. It might take some time to sink in, so this is why I'm leaving you with a program, and you guys can freeze the YouTube recording. You just type in the program. It's not really a whole lot of typing, but the most important part is what you do in GDB, because the static definition of the subroutine is not very interesting. I mean, you can stare at it all day long, and it's not going to do much good. It's only when you run the code in GDB, single step, and use BT to look at the backtrace to see where you come from, and then single step again to see where you continue execution. That is where you will start to understand, oh, so the recursion is really doing it this way. Okay. Now the interesting part is with recursion, subroutines, and ternary operators, we can pretty much do everything that we need to do. We haven't even touched on control structures. Okay, so let me show you what is in control structures. And in a certain, I would say, wicked way, those are not really needed. When you look at control structures, that's where you see all the conventional stuff that you have seen in cisp 300 and 301. This is where we talk about actual conditional statements. This is where we actually talk about repetition or loops, okay, which we usually know as while do, the for loop, or repeat until, or do while, that sort of thing. With recursion, you actually don't need any one of that. With ternary operators, you don't need conditional statements either. We're all done. Okay? And there are programming languages out there that would actually do this. They don't have loops. And the reason, I'm not going to prove it in this class, but there's a proof that says, recursion and loops, iterative statements, are equally expressive. So what that means is if you can write a subroutine using a loop, you can turn it into a recursive subroutine and get the same thing done. If you have a recursive subroutine, like the Fibonacci number here, you can turn it into a non-recursive subroutine using only iterations or loops, and it will get the same thing done. So one is not more expressive or more powerful than the other. The only question is which one makes more sense in which situation. That really is the question. All right. So I think I'm going to stop here. Oh, go ahead. Let me answer the question too.
I know nowadays, computers are way more powerful than they were back in the day, but on that level, is either one more efficient between a recursive? That's
a good question. So let me just repeat a question so it's recorded. So the question was, which one is more efficient? Is recursion more efficient, or repetition more efficient? The answer is repetition. Okay, that's a pretty clear answer. Recursion has overhead involved, where repetition has very little overhead involved. But the problem about repetition or using loops is it is difficult to prove your algorithm is correct. Okay, whenever loops are concerned, we get into a problem because the condition of a particular statement depends not only on statements that are before it, it also depends on statements after it, because after all, it is a loop, right? Yeah. So it is more difficult to prove the correctness of an algorithm using loops. But when you use recursion, on the other hand, and avoid the use of loops, it's easier because in mathematical proofs, there's a proof by induction technique that really lends itself to proving the correctness of recursive algorithms. So if you want to prove something to be mathematically correct, recursion is better. But if you want it to run faster, you want to avoid the use of recursion because it does not run faster. So that's a really good question. Yep. Any other questions? All right. If there are no questions, I'm going to stop the recorder now. If you guys have any other additional questions, you want me to look at something, I can do that. But the recorder is going to be off.